Hello everyone, welcome to this presentation on structure-aware hierarchical graph pooling using information bottleneck. This work done by me, Keshav Kumaran, and my co-authors Omit Roy, A.K. Mahabubama, M. Ashtapulamin, and Amin Hasan Ali. In a bird's eye view, a single graph pooling layer is to propagate feature across neighborhood and aggregate them and transport them into embedding space, and followed it by a pooling operation that construct a Coarser graph for the next layer. The key components of graph pooling are mapping method, that is how to map into a Coarser graph, and readout functions and objective functions. Existing graph pooling methods suffer from several drawbacks. That are first one is they are incapable of learning important local subgraph or community structures. In this figure, we can see that SF and deep pool methods cannot learn this structure properly, and in the other hand, top keep this pool actually fail to learn any kind of this property, this structure information. And besides, the simple classification without regularization term also may promote learning homogeneous node representation across the whole graph that impose naturally a challenge for simple pooling methods to learn local structures. And also redundant node features may also produce more homogeneous representations. Therefore, we introduce a hierarchical graph pooling method through modularity-based community detection to capture topological and functional substructures. In this figure, we can see that simple readout functions such as sum, mean, max, mean that fail to differentiate to substructures G1 and G2 with identical features. That's why we designed a structure-aware deep readout function to differentiate discriminative community structure. And we leverage the information bottleneck principle into the objective function to improve the expressive capability of pooling methods and to add in the resilience to adversarial attack. Here is the overview of our HIBPool. The input graph is first partitioned into several communities, and we apply message passing networks to propagate feature across the neighborhood, and then we downsample each community into a supernode and construct a Coarser graph of supernodes, and feature of each supernodes is computed through the deep readout function. Finally, we update the parameters of our GNN of our pooling methods by optimizing these objective functions, and we employ Loven algorithm to get optimal partitioning using this modularity. And after getting the optimal partitioning, we compute a mapping matrix M, where the M of IV equals to 1 when node V is in the community I. We use a special convolution to aggregate features from neighborhoods, and we use different weight W1 and W2 to give the importance self feature and aggregate neighborhood features separately. To develop or to design our deep readout functions, we utilize k number of topological features such as degree, clustering, coefficient, between centrality, and etc. Then we normalize the centrality values separately for each community, and then we scale node embeddings by the centrality values and concatenate them with no scale embeddings to get the expanded embeddings for each node Z till. However, we consider this community as a multi-set of node features, so we can compute a statistics over node feature within a community. In other words, we can compute some mean, max, mean of node feature for each community separately, and then we can pass these communities through an MLP to compute discriminative representation for each community. And therefore, to get the representation of whole graph at a pooling layer L, we can average of the embedding vectors for each communities. Then we can compute a Coarser graph using the mapping matrix M, And this equation ensures the connectivity of pool graph, where any two supernode I and J are connected if there is any S between node pair U and B, which are in the community I and J respectively. Let's derive our objective function. And due to interactability of general IB, we approximate our objective for each layer I as IB of A, X, Y, and S is equal to minus I of Y and S plus beta times I of AX and S. Here I means mutual information. We rely on the community dependent assumptions, that is pool representation SI only depends on respective community structure PI and inter-community nodes features, while being independent of the rest of the graph. With this assumption, we can simply estimate I of AX and S as the sum of I of AX SK, where K means communities. And following the current GIB, we set an upper bound I of AX SK and estimate the upper bound by using sample from a normal distribution, where the parameter mu and sigma square are to be learned through our GNN. And finally, we can rewrite I of AX is as log of P of is given AX and Q, and we can simplify this term as it is, and we assume that the given input features follows the normal distribution of mean 0 and standard deviation of 1 standard deviation. Then to estimate our second term in our objective function, mutual information of A, graph level U, graph level Y, and summary representation S. For this, we can use simple classification cross-entropy loss. And finally, these equations allows our model to utilize the benefit of IB principle to learn minimally redundant and maximally informative graph level representation. Here is a brief of multi-layer HIBPool and MHIBPool. And in multi-layer HIBPool, we stack multiple HIBPool pooling layer together to compute graph representation in hierarchical manner. And MHIBPool, in MHIBPool, we compute multi-resolution communities, and then we apply multi-layer HIBPool on them. And finally, we compute the final representation as a weighted sum of each layer summary representation. For multi-resolution HIB pooling, we use this equation 16, and we get multi-resolution communities through varying the value of the resolution parameter alpha. And to evaluate our model, we compare the performance on inductive graph classification tasks with decent baseline, and we conduct analysis of effectiveness of deep reader function and the effect of adding the IV, and further analysis on the resilience of our model against the feature perturbation. For our experiment, we use 6 popular graph classification benchmark dataset, and we follow 80-10-10 splitting ratio for training, validation, and test set. For baseline in our experiment, we use deep pool, K-plex pool, SAC pool, graph unit, min cut pool, LSAP, and GXNet methods. And in addition, we compare multiple variants of HIBPool in our experiment, which are HIBPool mean without IB, finds communities and apply mean readout, and optimize the simple classification loss. HIBPool deep readout without IB, it's employ deep readout under a simple classification loss. And global pool with IB objective, it's apply one layer message processing network and takes the average of all node embeddings to compute the graph level representation in a single layer. And random pool with IB means it replaces the community assignment of HIBPool by a random matrix M, and HIBPool which means that it replaces deep readout function of HIB pool by a simple mean pooling function. Here is the result of our experiment, and we can see that our HIB pool consistently outperform all baseline approach in all data set by a significant margin. Because our HIB pool can capture preserve the structural information explicitly through community detection, and can capture discriminative community structure through deep readout function, and it also able to minimize the redundancy by incorporating IB into the objective functions. On the other hand, the factors that lead existing pooling method to underperform are learned assignment metrics or top case selection strategies fail to capture structural information, and we can see in this table that deep pool and SF pool cannot capture the community structure. And besides, the lack of essential regularization turns into objective to learn better representation for graph classification is also another reason for poor performance of existing pooling methods. In this table, we can see that HIB pool consistently outperform HIB pool mean, which means that deep readout is more expressive to learn meaningful community structure than simple mean functions. On the other hand, HIB pool mean without IB and HIB pool deep readout without IB shows competitive performance to each other, which indicates that deep readout function suffered from redundant information under a simple classification loss, and it's demonstrated that IB promotes deep readout to minimize redundant information by imposing constraint on the preserved information of input data. In this experiment, we can see that deep pool and HIB pool consistently outperform the other two approaches, global pool and random pool, which both ignore the intrinsic community structure in the graph. And superior performance of HIB pool demonstrate that local pooling is essential to capture the local structural information and to produce better informative and distinguishable representation of graphs for classification. And in our experiment of robustness against feature perturbation, we add Gaussian noises following the equation 17, and we report the mean accuracy in these tables, and we can see that the performance of deep pool and SF degrades significantly. But our proposed HIB pool shows better resilience to the feature perturbation. We vary the value of resolution parameters alpha and report the average accuracies, and we can see that it shows best performance in 4 out of 6 benchmarking datasets. In summary, in this paper, we propose a novel community structure pooling method for graph classification that includes a discriminative pooling readout function to capture community structure, and it leverages information bottleneck into objective function, which promotes to learn minimally sufficient and maximally informative graph representation, and it helps to attain the resilience to feature perturbation. However, the model superior performance validates the following findings. Number one is local pooling are superior to global pooling in capturing important community structure, and second one is a sophisticated pooling function is required to preserve distinguishable structure, and it is very important for graphs with homogeneous node features. And last one is the IB principle promotes pooling function to learn distinct representations. Here are the reference, and thank you everyone for your time.